In this lecture, we're gonna look at the blockchain network simulator. So the blockchain network simulator is a peer-to-peer simulator. It's open source, and it tries to set an as realistic as possible setting. Basically, what we want to do is to validate it also with the existing blockchain networks to see whether this simulator achieves the same or similar characteristics as existing deployed networks. So on the consensus layer, we have several parameters, for example, the block interval distribution or the mining power distribution. And on the network layer, we have the block size. So how big the blocks are that are distributed over the peer-to-peer network, the geographical location of the nodes and the miners, the number of connection of the nodes and the miners, so how they are connected to each other. And then we have 4 different propagation protocols. Those are the propagation protocols that we've also seen in the peer-to-peer network lectures. So by looking at the real distribution, you can see basically that most of the relaying nodes seem to be in Europe, followed by North America, while most of the miners appear actually to be in Asia Pacific. That's likely due to the low cost of electricity as well as the labor cost. We can see that Europe only has less than 10% of the overall hash rate, which is unfortunate because it seems really that the majority of the mining power is in Asia Pacific. So you can find the simulator on GitHub /ArthurGervais/Bitcoin simulator. It's written in NS3 and it's C++ based. So we also have a website here where we exemplify then the impact of the block generation interval on the stale block rate. So if you look here, this is the stale block rate that we are have. For example, if we simulate a blockchain with a block interval of 1 second, we get quite a high stale block rate, right? While as we go higher and higher in the block interval, so a longer interval, we can see here the stale block rate decreases. If you look at the impact and the number of miners, we can see if we have 16 miners, and again here we vary the block size and the block interval, we can see then the resulting stale block rate. So I invite you to go to this website to check out the different dynamics of what happens when you increase the number of miners. There's actually surprisingly not a big impact if you change the number of miners, at least according to our simulator. So we did several weeks of simulation, and what we did is basically we take a block interval between 0.5 seconds to 25 minutes. That's the parameter range for the block interval, and we have a parameter range of 0.1 megabyte to 16 megabytes for the block size. We took the possible combinations and we quantified then through the simulator the stale block rate. And what we found is just an example. At 1 megabyte blocks and a 1 minute block interval, there's no stale block rate increase when compared to the standard Bitcoin network, right? So that's why the question is, how can you scale Bitcoin? So if you only look at the stale block rate, then you could say you could go from 7 transactions per second to roughly 66 transactions per second without sacrificing security, which is in itself quite an interesting result. So the simulator obviously isn't necessarily very accurate. There might be some. It's still a simulation. It's not a real world deployment. For example, we abstract away the TCP propagation, the TCP protocol. So this means that if there's a blockchain congestion, we just ignore it. There's like no fallback window, for example, for TCP. And there are a few other things that we had necessarily to do in order to optimize and to run the simulator in faster than real time. So there might be some. This is still a cautionary note saying that we did the best that we could at the time of conducting these experiments, but simulations are and remain simulations and are not real world experiments.